Today we're going to do part 2 to our introduction to limits. We'll start by analyzing the value of a limit. Here we have the limit as x goes to 3 of x squared minus 9 over x minus 3. This is asking us to find the value of x squared minus 9 over x minus 3 for numbers really close to 3. We can't just plug 3 in here. If we try to plug 3 into x minus 3, we would get 0. And we know we can't divide by 0. So this is why we're not just going to plug in 3 and see what we get. So instead, we're going to pick numbers close to 3. When we pick the numbers, remember we said we have to look at the left side and the right side when we do limits. So I picked some numbers less than 3. 2.9, 2.99, 2.999, and then I picked a few numbers greater than 3, but still close to 3, so 3.1, 3.01, and 3.001. What we want to do is plug these into x squared minus 9 over x minus 3. That can take some time, so let's make it easier by using Desmos. We're going to start by putting in our function. F of x is equal to, we want to put parentheses, that way it will keep the x squared minus 9 together. Close parentheses, divide by x minus 3. And then we're going to click up to this little gear that says edit list, and we're going to add a table. So there's some standard values in there, -2 to 2. We don't want that. We want to use the values we picked. So 2.9, 2.99, and 2.999. Then we had 3.1, 3.01, and then 3.001. You can see at 2.9, the value of the function was 5.9. At 2.99, we got 5.99. At 2.999, we got 5.999. So the closer I got to the value of 3, the closer the f of x value got to 6. On the other side, on the right side, I have 3.1, which gives me 6.1. I have 3.01, which gives me 6.01, and 3.001 gives 6.001. Again, as we got closer to 3, our f of x value got closer to 6. So let's go ahead and transfer those numbers over and say this is how we're going to write this, that the limit as x goes to 3 of x squared minus 9 over x minus 3 is equal to 6. Let's try another one. Here I have the limit as x goes to 2 of x over x minus 2. And again, we see that we can't plug in 2. I would have 2 minus 2, which is 0. Can't have 0 on the denominator, so we're going to pick some numbers close to 2. You can see there's kind of similar to the last one. I have 1.9, 1.99, 1.999. 2.1, 2.01, and 2.001. First step, put in the function. So I have f of x equals x divided by x minus 2. I go to my list and I say put in a table. And close to 2, I had 1.9, 1.99, 1.999. I had 2.1, 2.01, and 2.001. 2 happened to be on the list already, and it says undefined. At 1.9, I got -19. At 1.99, I got -199. At 1.999, I got -1,999. So as we got closer to 2, I don't have the same value. Actually, I can see the values are getting smaller and smaller and smaller. At 2.1, I get 21. At 2.01, I get 201. And at 2.001, I get 2001. This time, the closer I got to 2, the numbers got bigger and bigger. We could go over to the graph and look here, follow along, that as I get closer to 2, my numbers go up, 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 up. And if I go closer to 2 from the negative side, the numbers get smaller, smaller, smaller. So I put my numbers back into the chart so we can look at how the values are kind of scattered around and getting really small or really big. And what we need to write is what is our limit going to be? Looking at x over x minus 2, when I do the limit as x goes to 2 of x over x minus 2, we're going to write d and e. It does not exist. What we need is a quicker way to evaluate a limit. So that worked, right? Doing the chart works, but it's not the most efficient thing to do. So we want to be able to evaluate limits without creating charts for each function. So I'm going to throw some different properties at you. There's 8 of them. That's a lot. And some of them are going to seem like kind of obvious or like, okay, of course I would do that anyway. Why do you have to give me other rules? So let me put this down as this is foundational. What we're trying to get to is this bigger thing called a derivative. And to do derivatives, you have to have limits. And to do limits, I need to know some rules about limits. So some of these will be easy, and that's okay. Easy is good. Kind of hold on to these and think these are going to come back and they're going to be important and we're going to use them again. The most important of the properties is the last one. So we just have to get through the first 7 kind of quickly. So the first one is the limit as x goes to c of k is k. here k is a constant. So this says the limit of a constant is that constant. So nothing's changing. And that's the idea with constants, is constants don't change. So we could look at it as the limit as x goes to 5 of 12 is 12, or the limit as x goes to 19 of 100 is 100. And it's important to me that you see the answers are the constants, the 12 and the 12, the 100 and the 100. They have nothing to do with the 5 or the 19, right? The 5 and the 19 didn't do anything to the function because the function was constant. Sometimes it helps to see that in the real world. So let's try this. Think about streaming services. Like, we all have lots of streaming services. So I just picked Disney Plus as an example. Notice it costs $7.99 per month. The price does not change with the number of hours you watch it. So the limit when x goes to 0 of $7.99 is $7.99. So if you have this streaming service and you just don't watch it for a particular month, you're still going to pay the full price of $7.99. If you watch it like 10 hours a day, so let's say we watched it 300 hours in a month, we would pay $7.99. So the number of hours we use doesn't affect the price that we pay. And that's good news for us because we all like to stream things like crazy. And so that means we're not paying for that number of hours that we stream. So we like that idea of something being constant. Everything's not constant, so some things do change, so variables. So here's the limit as x goes to c of x. It will be c, right? So let's try that. This looks like the limit as x goes to 17 of x is 17. Same thing, x goes to -8. Probably not surprised that it's -8. So as the variables start to come in, you're going to see that we're just plugging in values. If we had addition or subtraction in our limits, then the limit as x goes to c of f of x plus or minus g of x is equal to the limit of f of x plus or minus the limit of g of x. This says if you have a bigger function with parts, you could break them into their individual pieces. The plus or minus says if it was plus in the beginning, it will be plus when we separate it. If it was minus, then it'll be minus when we separate it, like this. If I have the limit when x goes to 4 of x plus 12, we're going to get 4 plus 12. So we're adding because it said add, that's 16. If I have the limit when x goes to 10 of x minus 5, we're going to have 10 minus 5, and that's 5. So we're just plugging in the values that we get from the limit, plug it into the function, and evaluate. If I throw a coefficient in, so the limit is x goes to c of k times f of x, well, the coefficient could come out, so we could just remove it and say k times the limit is x goes to c of f of x, and k is a real number. You actually don't have to pull the number out. You just can just plug the number in and use it. So if I have the limit as x goes to 5 of 4x, we can just do 4 times 5 is 20. If I have the limit as x goes to -3 of 2x minus 7, I'm going to do 2 times -3 minus 7. That gives me -13. Again, we're just plugging values in, and you probably think like this is the same thing as just evaluating functions. You're not wrong. If it says multiplication, I have the limit as x goes to c of f of x times g of x. I can do the limit of f of x times the limit of g of x. And where this is all really heading to is number 6 that says the limit as x goes to c of f of x is f of c for any polynomial function f. So if I have a polynomial, which means I have some powers and coefficients and adding and subtracting, just plug in the number and get what you get. Let's try that. The limit as x goes to 2 of x squared plus 5x minus 8 will be 2 squared plus 5 times 2 minus 8. We plugged in the value of 2 everywhere it said x. You could grab your calculator or do it in your head, whatever makes you happy, and that will give you 6. Also, just a little bit different polynomial, the limit as x goes to 0 of 3x to the 4th minus 7x plus 12. I plug in 0. So I have 3 times 0 to the 4th minus 7 times 0 plus 12, which is 12. If it's a radical, so here I have the limit as x goes to c of the nth root of f of x, well, you can still plug in c. So I'll have the nth root of f of c. There are a little bit of conditions. F of c needs to be positive or it needs to be odd. So if I have an even index, so if I'm taking the square root or the 4th root or the 6th root, I need that number f of c to be a positive number because I don't want to have complex numbers. If n is odd, then I can take the cube root, the 5th root, right? So I can do odd roots of negatives or positives, but I can only do roots of positive numbers if the root is even. So say I have the limit as x goes to 7 of the square root of 3x plus 4, plug in 7. I have 3 times 7 plus 4, and then I take the square root. So 3 times 7 is 21, 21 and 4 is 25, square root of 25 is 5. Then I have the limit as x goes to 5 of the cube root of 2 minus 2x. Again, you're just plugging in the value, so I have 2 minus 2 times 5, and then I take the cube root. Well, 2 minus 10 is negative 8. I have the cube root of negative 8. That's negative 2. So this is the big one. This is the 8th property that we need to talk about, and this is the one where you make sure you write this down. So here I have the limit as x goes to c of f of x over g of x. It's equal to the limit as x goes to c of f of x divided by the limit as x goes to c of g of x. But super important here that g of x can't be 0. So 0 becomes a problem because we know we're not allowed to divide by 0. So I'm going to show you 0 3 different ways. So first we want to say in these different ways, I'm going to use the number n, and that's going to be some real number. I don't care what number it is. I just care that it's not 0. So in these cases that I can break it down to is case 1 is I could have n over 0. So if I get a number divided by 0, this will tell me that the limit does not exist. So if I plug in my numbers and this is when I end up with n over 0, I just say d and e. Flip it over, if I have the limit as x goes to c of f of x over g of x equals 0 over n, then the answer is 0. It's okay to have 0 in the numerator as long as I have a number in the denominator. And then this last case, if I plug in my c and I get 0 over 0, we call this indeterminate. This means you're going to have to do some more work, and that work is factoring, right? So that's the complete expectation, but you won't leave your answer as 0 over 0. We're going to keep going, so I'll show you that. So let's start with this limit as x goes to 3 of 4x over x plus 2. Plug in 3. I have 4 times 3 over 3 plus 2. 4 times 3 is 12. 3 plus 2 is 5. I get 12 over 5 and leave it as a fraction. The fraction is absolutely fine. If the fraction can be reduced, I want you to reduce it by 12 over 5 is perfect the way it is. Let's try x squared minus 1 over x squared minus 3x plus 2, and I'm looking at the limit when x goes to 1. Plug in 1. I get 1 squared minus 1 over 1 squared minus 3 times 1 plus 2. That's 0 over 0. Okay, remember we said 0 over 0 says we need to do more work. This is indeterminate. You're never ever going to write 0 over 0 as your answer. That's a good way to get something wrong. 0 over 0 is never your answer. 0 over 0 says let's look at it a little more. So looking at it is factoring. X squared minus 1 is x minus 1 times x plus 1. X squared minus 3x plus 2 is x minus 1 times x minus 2. Notice I have an x minus 1 twice. I'm going to cancel. When I cancel, I have x plus 1 over x minus 2 remaining. Now I can plug in 1. 1 plus 1 is 2. 1 minus 2 is negative 1. And that gives me a value of negative 2. Let's try the limit as x goes to 9 of 5 over x minus 9. Plug in 9 to start. I get 5 over 9 minus 9, which is 5 over 0. I have a number on top. I have 0 on the bottom. That immediately says to me does not exist. Let's try the limit as x goes to 2 of x squared minus 4x plus 4 divided by x squared minus x minus 2. Again, my first thought is let's plug the 2 in. I have 2 squared minus 4 times 2 plus 4 over 2 squared minus 2 minus 2. 0 over 0. We know what to do. We need to factor. This factoring is x minus 2 times x minus 2 over x plus 1 times x minus 2. We're going to cancel one set of x minus 2. So even though the x minus 2 is twice in the numerator, I only get to cancel 1 for 1. Now I have x minus 2 over x plus 1. The 2 gets to be plugged in. That gives me 0 over 3. Now don't just write 0 over 3. You want to do that one more step and go ahead and write that as a 0. 2 more. The limit as x goes to 6 of 3x squared plus 5 over 2x plus 4. First spot should be, let's plug in 6. Plugging in 6 is good. It's not going to give me 0. Just going to get some numbers. So I'm going to grab my calculator, do 3 times 6 squared plus 5 over 2 times 6 plus 4. I end up with 113 over 16. That does not reduce, so I say, well, that's my answer. The last one, I have the limit as x goes to negative 4 of the square root of 1 minus 2x over x plus 3. Once again, I plug in the negative 4. I put parentheses around the 2 times negative 4 just to emphasize my negatives here. I have this negative, which really I'm thinking like switches to a positive. So I have 1 plus 2 times 4. So 1 plus 8 is 9. So I'm going to have the square root of 9 on the top. And then negative 4 plus 3 is negative 1. So my answer is negative 3. Overall, what I want you to see out of this section is usually you can just plug in the numbers and see what you get. So the limits will be just like evaluating functions. The only exception is if you get 0 over 0. So if we have a rational, then you're going to have to slow down, look for how you need to factor it, see what they have in common, reduce it, and then from that reduction where you don't have 0 over 0 anymore, you'll get your limit.